third session. In our third session, material transformations, we'll explore physical transformations in materials for graphene folding to programmable soft surfaces, tunable and programmable carbon fiber, and active products. Please welcome our first speaker, Paul McEwen, professor in the Department of Physics at Cornell University.
Well, thank you very much for inviting me. This has been one of the most interesting conferences I've ever been to. It's super fun, certainly one of the broadest ranging. I'm going to talk to you about something called graphene kirigami, and I should start off by mentioning that this is really the work of quite a large number of people at Cornell, both in my own group, but also in the group of Ji-Woong Park and David Muller. But let me start by just kind of telling you what gets me out of bed in the morning, why I'm excited about this field. And that basically goes back to an MIT undergrad named Richard Feynman, who told us basically 50 years ago what we should be doing, 60 years ago. He said, well, you should go out there and you should miniaturize information in computing. We collectively listened. That gave us the information revolution, and we all know where that got us. Next up is to miniaturize machines. He said we should do that, and that one, honestly, we just simply have not done. We've done a little bit of it. You've heard some of it here. Robert Wood's talk earlier today was a classic example of the miniaturization of machines. But we're really at the early stages of that process, as a lot of the speakers this morning have indicated. And it's kind of too bad, because small machines are at least as interesting as small information. And to quote Buzz Aldrin, you know, you promised me nano-submarines, instead I got Facebook. Actually, he said Mars colonies, but that's all right. You know. So, you know, why haven't we done this? Why haven't we made small machines? Because it's a lot harder. Miniaturizing information is rather straightforward, because information is basically scale invariant by its very nature. However, machines, when you scale them down, often they don't work the same way. If you shrink a truck, it's not going to work the same way as a truck at the macro scale. But there is a manufacturing technology that's pretty scalable. And for example, it's represented here. And it's a really cool manufacturing technology. You start from a plane. We really like working with things that start off in sheets. You make a bunch of lines in it, and you fold it up. And it's really simple, because it's completely obvious what this folds up into, right? Well, maybe to one person, but to most of us, yeah, correct, it folds up into an elephant. And what is interesting about this fabrication technology from the point of view of this talk is that these kinds of origami, these paper arts, this idea of taking two-dimensional object and folding it up, scales. So if you can do it at the macro scale, you could shrink the origami artist and the paper down, and if you shrank them all in exactly the same way, the technology would still work. And in essence, I think that's why this meeting works, is because these approaches to doing this are all scale invariant. It's just, to a first approximation, geometry. So this, if you're a nano person, immediately brings up a question. Well, you know, what does this look like? How small could you get? If you scale everything down, how small is it possible to go in this kind of approach? And well, you know, the answer is, of course, set by the size of atoms. If you scale down to the smallest sheet of paper you can imagine, you would have, say, a sheet of graphene, okay? And recently, there's been a great deal of excitement in doing all kinds of fun stuff with graphene. It's a very interesting electronic material. It's an optical material, you name it. But it's also just a really robust, nice one-atom thick sheet of paper out of which you can imagine doing the smallest kind of paper arts possible. And I should also mention that graphene just doesn't come in one flavor. There's a bunch of 2D materials that are being developed, all of them very old materials being made new again by being explored in single sheet form, all the way from single atomic layer sheets of glass to things that are basically semiconductors, insulators, and even now people are thinking about and doing vertical and lateral heterostructures of these materials. So making 2D sheets that mix materials, layering them on top of each other. If you think about this from a paper arts point of view, there are lots of things that you could imagine doing. And so the question becomes, you know, can we do this? Can we do some sort of paper art type three-dimensional structures starting from this two-dimensional material? Okay. So that's the question that we've been asking ourselves in my group. We will not fold this for you by the end of this talk, so don't expect it. But we are making a little bit of progress, and I'm going to tell you about that progress. So first off, you have to understand your starting material. And the first key question is how stiff is it? If I bend it, how bendy is it? Because basically the reason we want to shrink the paper in the Z dimension and make it 1 atom thick is because it needs to stay nice and flexible even when it's extremely small. Okay? So how do we answer this question? Well, first off, there's a whole fabrication technology that we can use to pattern graphene, and that's illustrated by this picture here. This is an optical micrograph, and if you look carefully, you can see, for example, a swirly pattern. That swirl that you see is a monolayer of graphene seen in an optical microscope. The dark things are gold pads that are attached to it. Some of these things are little cantilevers, so there's a very faint atomic layer sheet there with 2 contacts on it, and we can go with probes and pick up on these contacts and play with the individual sheets. And for example, to measure the bending stiffness, we'll just pick up one of these little objects here, and I'll show you what that looks like. So there's a pad, and there's a little graphene sheet between it. You can barely even see it here, but it's there, and that becomes obvious if you use a probe to grab this one and lift it up off the surface. It dangles down under the weight of the gold pad, and so there's a strip of graphene that's connecting those two, and by the amount it bends down, you can easily measure the bending stiffness of graphene. By the way, a couple of comments about this. The size scale, these are like 10 microns or so. So, most of the origami stuff that you've heard about in this meeting so far would be orders of magnitude bigger than what we're talking about here. This is really in the sort of 10 micron scale limit, spatial limit of what we can do. The second thing is this is all in water. The other thing about scaling things down is everything sticks to everything else because of van der Waals forces, so you have to put stuff in water and put in surfactants to keep things from sticking to other things. We don't know of a nanotechnology that doesn't exist in water. All of biology exists in water for exactly this reason. So there's another cheat hidden inside of this. Anyway, if we accept we're going to work in water, we can measure, for example, the bending stiffness of these graphene sheets. And this is the spring constant of this graphene sheet. It's a function of how long the graphene sheet is. You don't need to pay a whole lot of attention to this graph other than, number one, we took a whole bunch of data using a whole bunch of techniques. And number two, this is what we got, and this is what we thought we were going to get. And finally, this is a log scale, so we didn't miss by a little. We missed by about 3 orders of magnitude in how stiff the graphene was in comparison to what we thought. And the answer is it was a lot stiffer than what an atomic scale person would have told you. People know a lot about carbon-carbon bonds. A chemist could tell you what the stiffness for bending carbon-carbon bonds is, but our paper came in about 1,000 to 10,000 times stiffer than what people thought. And so, why is that? It turns out the answer is incredibly simple. There's the answer. A crumpled sheet is much, 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 much stiffer than a flat sheet. So we thought we'd made that, when in reality we had made that. And since the bending stiffness of a sheet of paper goes like the thickness cubed, if it's crumpled, it basically acquires a thickness that is the size of the crumples, and it gets much stiffer. In fact, we went in and were able to image these crumples by using Newton's rings, a kind of interference microscopy. So this modeled pattern you see here of the graphene between these 2 pads is due to the height variations of the graphene sheet. Now, I should say we don't know why it's crumpled. We didn't mean for it to be crumpled. We don't necessarily want it to be crumpled, although we don't really mind, but it is. It's another one of these things. First, you got to understand your raw material. And I could give another talk on why it might be crumpled, but I'll save that for another day. But this stuff does act like paper, and in particular, it acts like a certain sort of paper. So this is a graphene sheet that I'm going to push on. And you can see that it will bend and flex like a sheet of paper, buckles and what have you. But it's not quite like a sheet of paper, and you're going to see it's not quite like a sheet of paper in the following way. If you reverse it, it all goes back. It's an elastic sheet of paper. Okay? So that's kind of cool. It makes for a neat video. It's sort of neat. If you're an origami artist, it's kind of bad, right? Because there's no creases. So we're not going to show you origami because we don't know how to crease an atomically thin sheet of paper. If you do that, that's called chemistry. You would have to go in and modify bonds or something, or start stacking layers. That's also another talk. But there is something we can do in the paper art realm that works perfectly fine with elastic paper that doesn't require creases, and that's so-called kirigami. So kirigami is origami if you don't have any standards and you're allowed to cut the paper as well as fold it. And once you do that, the world opens up into a much broader space. And in fact, you can make very simple things. Some paper models are shown here, and then realize them in their graphene versions down here. And that's what's shown here. By the way, these paper models are not just for visualization's sake. As I told you, everything is scale invariant in this kind of approach. So if you get the ratio of the length to the thickness of the paper right, it'll act about the same way as these models. And it turns out for the size of these things that we're making in graphene, about 10 microns or 20 microns long, the effective length to width ratio is comparable to a standard sheet of paper. So we play with the paper models, and that actually informs what's going to happen in the actual microscale system. So that's kind of fun. So what actually happens, can you do this? Well, I'll just pick out one of them for now. I'll pick out this one here. This is a spring where it stretches by bending, as you will see in just a second. So the paper model, there it is. You can stretch it, and it does this cool thing. It buckles out of plane when you pull on it. Spontaneous symmetry breaking going on. There's all sorts of fun physics there. But if you ignore all that and just say it's a soft spring, the question is, can you make it out of graphene as well? And the answer is yes. And so you can pull on it, and it stretches just like the paper version. And it's very robust. You can do this as long as you want. You can do it thousands of times, and it will just keep doing it as long as you don't pull it so hard that you rip the thing apart. It's really quite amazing. And I'll mention, by the way, the spring constants for a spring like this are about 10 to the minus 6 newtons per meter, which is incredibly soft. It's like 1,000,000 times softer than a typical atomic force microscope cantilever, for example. These are some of the softest springs made out of these kinds of materials ever made. So that's pretty fun. You can also make nice images of these. You can scan the focus of your microscope and really look at the 3D structure of this thing. There's a bacterium or something floating over there. And you can compare them in some detail to the paper models. This sounds ridiculous, but it's actually useful to do. We do these fancy, micron scale optical resolution of these structures, and then we compare them to the paper models, and they do all the same kinds of things. It's really fun. But I'll mention this device is not just a mechanical structure, it's also a transistor. Graphene is a conducting material whose conductance is a function of the induced charge on it. So we can also attach electrodes to this and measure the conductance through this thing as it stretches. And I won't belabor this point here, but suffice it to say that when we stretch it, the conductance properties don't change because basically the atoms aren't changing. Nothing's happening. It's just sort of changing its form into a more convoluted structure. But this is very exciting for things like soft electronics. You may have heard about wearable electronics where people want to tattoo really soft stuff on your skin. Think of this as wearable electronics for the individual cell. It's soft enough that you could put it on up against a cell, and the cell wouldn't mind it in the same way you wouldn't mind one of these wearable electronics tattoos. So we're looking into that for neural recording and what have you now. But just to make the point one more time about how soft these things are, we can actually put like a little mirror on top of this graphene structure, shoot a laser from below, and that will cause the structure to lift up just from the pressure of the photons hitting the little mirror. So this little pad here, I think in a second it will, or maybe it already did, it will go up and down as we turn a laser underneath it on and off. So the pressure of photons, piconewton scale forces, can cause large displacements in these structures and allow you to even calibrate what kinds of spring constants that you have. And the other thing I'll mention is you can also manipulate these things magnetically. For example, in this case, we put a little magnetic pad on here, and we can twist it and play with it and cause the graphene to fold over like you see here. And what I'm building to is we can start to take all the other kinds of technologies that we have, other electronic materials, magnetic materials, optical materials, and attach them to these graphene sort of scaffoldings, this graphene backbone, and make all kinds of devices. And what's it good for? What are these graphene things good for? Well, here's a really boring example. You can make a graphene hinge. So in this case, there's a thin sheet of graphene between these two pads, and I can open and close this hinge with, again, piconewtons of force and make a hinge that is scalable down to this micron scale. which turns out is not that easy to do. Ask your favorite MEMS person to build you a hinge that will work on a micron scale, and it's not easily done. Because basically you're going to have to narrow something down to the atomic scale to get the kind of flexibility that you want. And as I said, these things are incredibly robust. You can open and close this hinge forever. And so we're really starting to think about taking these kinds of hinges and implementing on the graphene, on top of the graphene, all kinds of functionality that you might find interesting. Then you can fold the thing up, deliver it somewhere, and then have it do something in an interesting environment. So we're beginning to think of the graphene or these other 2D materials as a backbone upon which you can put all of your existing technology, fold it up into an interesting shape, and unfold it as needed. So we're just at the start of this game. We're just beginning to learn how to do this, but we are getting somewhere. And I think over the next few years, you will see more and more of this kind of stuff come to the fore and really be, it's really a great opportunity to try to push all the stuff that you're hearing at this meeting down to the smallest possible scales. So with that, I will thank you.
Thank you. Let's welcome our next speaker, Pedro Reis, Associate Professor of Civil and Environmental Engineering and Mechanical Engineering at MIT.
Okay, very good. Is this on? Excellent. Well, thank you, Skyler, for the invitation. This has been an amazing series of talks so far. I'm afraid you might hear the boring engineering talk now after all these wonderful design talks, but I'll try my best. So in fact, the previous speaker already mentioned the name of my lab. So he talked about elasticity. He talked about geometry and scale invariance. And the talk that he didn't talk about, that he said when you crumple a piece of paper, he would have talked about statistical mechanics. And that's the statistics here. And so we look at these kind of problems as well. We focus on thin, slender structures where the geometry is scale invariant. And so rather than working at the graphene scale or the kilometer scale, and we are motivated by problems at both of these scales, we scale them down or up onto the desktop and do precision modeling experiments towards predictive understanding. And so the goal is then to harvest instabilities of these structures for functionality. Now, today I'll be focusing on one single problem where we're going to get inspired by the wrinkling of fruit and develop some precision samples where we can excite these dimpled wrinkling patterns, which look remarkably similar to the dimples on a golf ball. And then we're going to say, wow, this might be able to be used as active, switchable and active drag reduction surfaces. So since I mentioned golf balls, let me start with a brief history of golf. So golf actually dates back to the mid-1200s in Holland. Monks were hitting stones with sticks. Then golf balls evolved to wooden spheres, eventually to leather with feathers inside. And then wax started coming from South America. And so wax is much more ductile. And the issue with these balls is that each time they get a hit, they develop a dimple. Then you make another hit, they develop another dimple. And so the time was actually custom in the mid-1800s to play with very smooth balls in tournaments and to practice with dimpled balls until the story goes that in one tournament is the Tiger Woods of the time, so Old Tom and Young Tom, they were actually father and son. One of them ran out of dimpled smooth balls. He had to use an old ball and they actually went much, much further. And that's where I went, haha, there's something here. And then we end up with the design of the golf ball today. And the reason is in the mechanics of fluids past a bluff object. And so if the sphere is smooth, the fluid goes around, at some point it separates. And there's a turbulent region at the back that is the source of drag, or form drag, which is different from skin drag for highly streamlined objects. So form drag. Counterintuitively, when the ball is rough, there's actually a detail on the boundary layer that gets stripped from being laminar to turbulent. And the separation point actually occurs later. The turbulent region is smaller, and as a result, drag is also lower. So let me take you through these plots. So this is very classic data from Achenbach in the 70s. I'm plotting drag coefficient as a function of Reynolds number or flow speed. The blue curve is for a smooth sphere, so the drag remains fairly high in the range of around 0.5, which can be calculated exactly over the range of, for which golf gets played. By contrast, a golf ball has a drag crisis much earlier, and over the range of golf actually has a lower drag by a factor of 2, so drag is 0.25. And if you play with the roughness of the sphere, you can have a different kind of behavior. So motivated by these, we're now going to exploit wrinkling of curved objects. But before I talk about curved objects, I really should give a little introduction on wrinkling. It might be trivial for some of you in the audience, but maybe not for others. So wrinkling is what you see literally when you compress a thin, stiff layer on top of a soft substrate, like skin on top of flesh. And I'm not using technical terms. I don't know them. So we have a thin, stiff film on top of a soft foundation. When you apply a compressive load, the thin film, perhaps if it was by itself, not perhaps, if it was by itself, we would like to go on to first buckling mode, but it's attached to the substrate, so that would cost too much energy. And instead, there's a characteristic length scale that gets selected, that looks like this in real life. It has been calculated exactly, so the solution for wrinkling dates back to the 60s, when people were thinking about sandwich panels in structural applications. And so the wavelength for wrinkling depends on the ratio of the stiffnesses of the film and the substrate to a power of 1/3. It goes linearly with the thickness of the stiff film, and there's a prefactor that can be calculated exactly. So this is for uniaxial compression. When you apply loads biaxially, so you have loads in two directions, you can get more complex patterns. And the recent analysis by, where is his name, John Hutchinson at Harvard, and these studies from a few years ago, from 2011, he showed that for wrinkling of flat plates on a flat substrate under biaxial compression, there's multiple solutions, but all of these cost a lot of energy, and the one that you're most likely to see are these herringbone or fish bones kind of pattern. And so keep this fact in mind because we're going to revisit later on. Okay, so we wanted to look at wrinkling on curved surfaces. So the research question is, how does the curvature of the underlying substrate affect what we know about wrinkling on flat systems? So how we make these samples is kind of interesting. We do not use bacteria, unfortunately, but we have a thin, stiff shell on top of a soft sphere with a cavity. So think of it like an avocado. You have the green, thin stuff on the outside, and then the stuff that you eat and the bone. You get rid of the bone, so you have a cavity. And we're going to depressurize this cavity in order to apply compression. So it's actually, well, just a little aside. So this is actually turned into a project of its own. How do we even make these thin shells, which are not graphene thickness, but you can also not make them by casting? We use a coating method where we pour these polymers over a curved surface. They're getting thinner because of drainage, but there's a magic balance between gravity, polymerization rate, and viscosity, such that the thickness that we get is constant within 5%. It's magic. You'd have thought that the top would be thinner than the bottom. That's not the case. And so we can actually design for shells of different thicknesses, and we know the parameters, how it depends on viscosity, on the radius, on the curing time, and so on. Anyway, so knowing how to make these things, we can now tune parameters for the shell and for the core. We work over a range of stiffnesses over a factor of about 100. And when we depressurize these samples, they actively switch instantaneously, so this is not through swelling, it's through pneumatics, so they're fast, and we can excite these dimple patterns. And this is where we saw the analogy, there might be something here that connects to golf balls. But before we get there, let me briefly tell you how we can tune parameters in order to get different patterns. So first of all, if I plot the wavelength that we get in our experiments, as a function of the prediction for flat plates, you have a y equals x line. And so basically what we get on our curve system is exactly the same for the length scale, for the wrinkling wavelength, than what people have calculated for flat plates. So that was a bit of a disappointment. On the other hand, we now have a design guideline. If you want dimples of a certain size, we know how to get them. Now, the fact that we're seeing these crystalline dimple patterns, which would not have been very easy to see at all, other than a very small region of parameter space for flat systems, here now they're very prevalent. So if I plot a phase diagram with ratios of stiffness between the film and the core as a function of the ratio between the radius of the sample and the thickness of the shell, there's actually an extended region here over which we see dimples. So curvature is modifying the pattern that is getting selected. Now, this is probably the slide with the largest number of equations in the conference, so I apologize. But so first, let me give you the results. So the question is, why do we modify the result that we obtained for the flat case. And this is work done in collaboration with Jorn Dunkel from the math department at MIT, again, with two wonderful postdocs. They really developed this model. These are our experiments, so we can get either dimples or an intermediate mixed phase or labyrinths, and they can predict that exactly. This is the same phase diagram that I showed you before. So now we can put theory on top of experiments, and theory lines very nicely separate the various phases. So we have predictive value here. And I think I'm actually going to skip this, so since I'm running out of time. By the way, there's the kind of mathematics that goes into describing wrinkling of this system is very, very, very similar to Rayleigh-Bénard convection that happens when you heat up a hot fluid on top of a cold fluid. You get these vortices, and you can develop patterns that way, and so it's essentially the same mathematics. That's what the previous equations were showing. So this is probably the simplest program that we've seen in this conference so far, and so I can program my structure either by targeting one of the modes. So let's say I want an hexagonal mode. I know exactly the parameters that I need to find to get this hexagonal mode. If I want a certain wrinkling wavelength, well, I know how to do that as well. And then I can run my program, meaning that here I'm plotting amplitude of the dimples as a function of depressurization. And so I can target a certain amplitude for the dimples on demand and in a nearly instantaneous manner. So this is where the analogy now comes in. So we know how to design the thing on the left, and we want to see if we can do something with the thing on the right. So we took our smorfs. By the way, we call these things smorfs, smart morphable surfaces. So not Smurfs. Smurfs, apparently, they never wrinkle. So I learned. I had a Belgian postdoc who knew about all of comics. Anyway, we took our samples for a test ride in the wind tunnel here in the Aeroastro department. Our setup allows us to, so we have wind blowing from left to right. These are our samples. They are connected to a vacuum chamber here, a depressurizer, through a hollow pipe. They are held by this air bearing. And so this is the T-splitter that connects to the vacuum chamber. And then we have a force sensor here that allows us to measure the force that the wind exerts on the ball. So we can measure the drag force, from which we can calculate the drag coefficient. Is defined like this. So it's just the drag force divided by a bunch of things. Reynolds number is identical to saying how hard I'm blowing with a wind tunnel. And so this is a wonderful plot that tells us that for the same sample, so I'm not changing samples. This is for one sample, and I'm depressurizing it. So different colors means different states of depressurization where I'm changing the amplitude. And so as a function of wind speed, I can go for smooth samples all the way from a high drag of around 0.5, which what I had shown from the classic results from the 70s. And I can switch these structures to show a much lower drag, around 0.3 or 0.25, so nearly a factor of 2, just by depressurization. And so we can get approximately 50% dynamic drag reduction. So now if I fix the wind speed and I change the pressurization, we see that I can smoothly tune the drag coefficient. And this could be nice because now we can start to think about control. So let me answer the first question already. What could this be useful for? So we might envision designing structures that are coated with this smart surface that could have a lower aerodynamic drag. This could be beneficial under storm conditions, for example. So we might think about affecting the boundary layer next to the wing, the airfoil of an airplane, perhaps to change drag and lift. An even more concrete application is perhaps to play with a region where the flow separates from a car, and we might be able to reduce drag in these structures, therefore increase fuel efficiency. And in fact, this sounds silly, but Mythbusters, which is very serious, actually went and checked this out. So they cast a car with all these dimples, and they were able to show, Mythbusters show, they were able to show that they could reduce drag, they could increase fuel efficiency by about 10%. However, they had no way of knowing what dimple size to optimize for and so on. And so I think with our design tool, we might be able to get there. And we're actually currently actively working one of the leading car manufacturers, but I can't really tell you too much more about that. Okay, so what's our vision? Where could we go from here? And this is where I think active matter can really bring an example that it can really bring us something more than static matter. And so let's go back to the plot by Achenbach. So these are drag curves as a function of wind speed for different roughnesses. So very, very high wind speeds, the smooth ball will always have a lower drag, so will always be better. at lower wind speeds, the rougher the ball, the better. So what by having an active surface might allow us to have is that if, depending on the wind conditions, we're able to actively tune on demand the roughness of our surface by knowing where you are, we can actually ride the surface of minimum drag. So you're able to get the surface with lower drag by being active than any other static surface. And I think this is exciting, and we're very actively pursuing this right now in our lab. Okay. So to conclude, I told you about these experiments in a scaled environment at the finger scale to explore the mechanics of thin structures. And I gave you this simple example of wrinkling on a curved surface. So curvature comes in and affects the process. I introduced you this concept of SMORFs, or SMARF morphable surfaces, that can be exploited for switchable and tunable aerodynamic drag reduction. And this was just an example of one of the things we're doing in our lab. In a number of other problems for plates, rods, and shells, we're employing the same mindset of doing very precision experiments at the desktop towards learning the underlying mechanics that we can then exploit as design guidelines for either very large length scales or small length scales. And so I'll finish by thanking my wonderful team and thanking funding from NSF. Thank you. And I get a minute.
Thank you. Our next speaker is Yin Liu, postdoctoral research scholar in the Department of Chemical and Biomolecular Engineering at North Carolina State University.
Good afternoon, everyone. Can the people on the back hear me? So it's our great pleasure and honor to be here, be invited to this wonderful event. And although my PI supervisor, Professor Dickey, cannot make it, but I will here to present our group to try my best to give you highlights for all the shape programmable materials studied in our lab. So first, the nature actually already demonstrates a lot of amazing plants or living animals for the shape programmers. You probably see some of these examples this morning, and also a lot of DNA programming in this afternoon. So here is another examples for the plant called flytrap. So this is taken by the fast speed cameras. So when this plant got some stimuli by the environment, actually it will change the curvature of itself, and eventually it will fold up and close to trap some maybe fly inside. So in our group, those materials we are interested, which can realize the shape programmable, is from liquid metal, hydrogel, to shape memory polymers, which is from the nanometer scales, micrometer scales to millimeter scales. So first thing I want to talk about is the self-folding strategies, which is I'm working on with co-advice with Professor Young Ganser in our department. So we're interested to convert the 2D dimensional pattern into 3D structures by self-folding, because it can be compatible with a lot of conventional 2D patterning technologies. So here is an example. I actually bring some samples with me. So what we use is kind of like this flexible, transparent polymer sheet. We use just a regular printer, which we can pattern this black ink as a template on this polymer sheet. So in this video, I will show you quickly. So this is a template we cut out from these materials. Sorry. After exposing to some IR heat lamp, you can see it will fold directly into 3D structures in seconds without hands facilities. So the point is actually the pattern printed black ink will absorb selectively the light, and then convert into the heat to locally heat the polymer, cause the shrinkage. So I will explain a little bit more about these materials. So this materials is actually biaxial stretched polymers, which is flexible, transparent. Maybe you already heard the children's toy called Shrinklings. This is one example for that. Usually, when you put in the oven, by applying the uniform heating, you will get the final single shape, which becomes smaller. In this case, it's about a 50% shrinkage. However, in our method, we're using the light and printed the black ink on these polymers. In this case, we can achieve many different origami structures by applying different geometry, hinge geometry or patterns. So actually, this process can be further controlled well by control the geometry of the hinge and also the hinge width. We are actually also interested to see how we can implant these 3D structures or self-folding method to produce some functional device. So we did test the preliminary to pattern this kind of like silver film on these 3D self-folding structures. And we also collaborated with the electrical engineering at NC State to build up the prototype for the antenna. So you can see we actually just simply pattern this copper foil on these self-folded structures. After exposing to the IR heat lamp, actually it will fold. By characterizing the antenna's properties, you will find the signal for the antenna actually shift. I will not discuss the detail for the data, but here the point is it can be potentially applied to some sensors or other like reconfigurable devices. Then you will think about that, whether this method can be applied in other ways, for example, changing different light source or ink absorbers or different materials. Actually, that's one thing we're interested to explore. So one example is instead of using IR heat lamp, which you can find it in McDonald's or your bathroom, one thing we use is the laser folding. We collaborated with one optical group in electrical engineering. So this is basically set up. So actually, all these lens will convert like an IR laser from the spot to the linear pattern as illustrated in this cartoon. So after I remove this block, you will see these black coated shrink films will actually bend to 90 degrees in seconds. So these things compared with the original IR heat lamp and black ink, the cool things is no require for the pre-patterning the hinge on these materials. So actually, the people in electrical engineering, they are able to program the path of the laser light. So in that case, directly program the laser light so you can predict how the hinge folds. Another thing is about ink absorbers. So we're using the regular black cartridge ink, and also you can think about other possibilities. One thing we're thinking is kind of like relevant to today's talk and also interesting is the microwave heating. So this is work has been done by a grad student in our group. So basic idea is similar. So we're using screening printing to pattern this graphene ink on these same materials. So by applying the microwave, actually you can also realize the local heating for these materials to cause the foldings. So I want to mention that so actually we tried the power is from 40 watt to 250 watt. Just to remind you, so commercially microwave in your kitchen is about 700 to 900 watt. So this is quite low. And the process, although I don't have video shows here, so it's actually folding will happen at room temperature in seconds using this low voltage. And also similar hinge width can control the folding angle eventually. So I mentioned that this materials actually is biaxial and commercially available. So we're thinking, how about the pre-strand is unsymmetrical? So how about the uniaxial pre-stretched polymer sheet? So actually, you will find some very interesting phenomenon different from the previous shrink films I showed. So which is actually the behavior will depend on the strain directions about that. So for example, if you pattern this hinge, actually for this demo, we actually simply use the Sharpie marker to draw this black hinge. If it's perpendicular to the strain direction, you will also get this sharp folding as well. However, if your hinge is parallel to the strain, you will form these rolling structures or this like a candy wrap shapes like that. So although we are interested in fabricate 3D structures, but actually these materials is also cool to realize some 2D shape programming. Because the strain is only one direction, it's not symmetrical. So actually, depends on how you cut the polymer sheet compared with the direction of the straining, you can achieve different final shapes by simply cutting it at the different directions. So this can be future maybe applied. We propose some interlock structures, or you can think about other possibilities to apply it to other materials. So this work, as like a lot of great talk at beginning, previous about the design, our team actually also diverse. Although I already demonstrated we collaborated with electrical engineering, we also work with mechanical engineering to study some mechanism models about this folding process. And also we work with the College of Design at our school to study how it's possible to combine the self-folding strategies to some textile or fabrics to form some interesting design structures for that. And also another thing is we collaborated with some local high schools to try to educate like high school students, and we done a lot of demo and outreach using self-folding to try to educate those like middle school students. Actually, this afternoon there's a nano days in our campus, so I cannot join it. So besides this self-folding, the second thing I want to talk about is really cool ideas in our groups, which is liquid metal. So as you might know, like in chemical periodic tables, gallium has a melting point near to the room temperature. But when it's added with indium, can depress the melting point to as low as 16 degrees. So that means it will be the liquid in the room temperature. As you see in these videos, actually, this liquid metal can be painted and moldable. So the key point is actually there's a few nanometers thick of oxide skins will form instantaneously in the air on this liquid metal to kind of like dictate the properties such as the shape of these liquid metals. However, actually you can also, by adding acid, in this case one more HCl, then you can actually remove the skin on the liquid metal, so finally it will behave like a mercury, so beat up. But these materials, compared with mercury, is no toxic, or we will see is a low toxic. So one thing we can do using this liquid metal is do some 3D printing. So as you see it here, we can 3D print this liquid metal droplet. So this is actually the oxide skin. Because this skin has enough mechanical properties, so it can hold these structures and stacked up to each other to build up different 3D structures. Now you can think about to combine this 3D printing to other materials, which can be done at the room temperature. So in that case, you can come up other many cool ideas about that. So actually, the students spend a lot of time to build up this stage. And besides the droplets, you can also build up these wires. Since it is flexible, stretchable, and conductive, so it can be used as an interconnect. So accidentally, there is a dead bug. We didn't kill it, but the student decided to do some simple demo on this. Although there's no real function on that, but it shows how, yeah. Personally, I'm scared of this kind of bugs. But it shows how small the scale is and how gentle the process can be. So you can find this on the YouTube. So another thing is you can control the flow of this liquid metal by actually more complicated adding voltage in the electrolyte due to some electrochemistry. I won't go details about that, but I want to show this video for you. So by applying small voltage, positive voltage, actually this liquid metal will from the droplet instantaneously to go to this pancake shape, which implies that the surface tension has dramatically decreased. We propose that is because the oxide skins start to behave like a surfactant to lower the surface tension almost to zero. So there's many other examples can be applied using liquid metal since it's flexible, stretchable, and conductive. And also you can use it apply to some other reconfigurable devices. Another last things I want to briefly mention is the one work for the hydrogel folding collaboration with Professor Olin Valovs in chemical engineering. So we're using is one called electrolyte hydrogel, which has this ions inside. When you apply the voltage by using this copper electrode, the copper ion actually locally forms a complex to this hydrogel, and meanwhile release water. So the hydrogel will locally shrinkage to cause this bending. So by applying the different times for this folding, you can achieve larger folding angles like that, as it shows here. So just to remind you, our group is interested in shape program materials like liquid metal, hydrogel, and shrink films. So we would like to thank all our group members and our wonderful collaborators for all this interesting and exciting work we've done in our groups. Finally, I would like to thank our funding agencies. If you have further questions, you are welcome to contact my PI. And yeah, thank you very much. Yeah.
Thank you, Ying. Our next speaker is Yunus Khan, founder of Carbitex.
So I've been traveling for about 8 weeks this year so far, so I have some cheat sheet notes. I was back at our facility for about a day prior to heading out here. Really appreciate the opportunity to be here, and thanks Skylar and Athena and the rest of the self-assembly lab. First I'd like to say that unlike all the other presenters here, my background isn't in science or engineering, architecture, or art. It's in the comparably dry and boring field of economics. However, as a founder of Carbitex, I'm ever curious, I'm passionate about progress, relentlessly optimistic, and I think those are characteristics that we all share. So needless to say, I'm very humbled and excited to be here. So my topic today is tunable carbon, specifically how it relates to material transformation. So during my time today, I'll talk through several topics, just give you a little bit of an overview about Carbitex, our technology, the collaboration we have with the self-assembly lab at MIT, and then some new developments in matrix placement, zonal composite, shape memory, and fiber orientation. And the theme throughout this is going to be kind of bridging the gap between research and mass market application. So Carbitex is an advanced materials company that focuses on the development and the manufacturing of flexible carbon fiber composites. And we do this at our facility in Washington State, where we have a development lab, analytical and testing lab, and manufacturing capabilities. Our development lab really focuses on the development of matrix materials, as well as various processing techniques that we develop in-house or are variations of coatings, laminations, impregnations, and curing. And our testing lab is set up for a host of mechanical testing capabilities, as well as like product lifecycle capabilities, because we're a company that focuses in consumer goods as well as the industrial and commercial market. And our lab, or our production facility, is set up in a way to kind of mimic a larger scale of our lab capabilities. So this kind of Venn diagram shows where Carbitex fits in the role of active matter anyway. And we fit somewhere between that fundamental research and the mass market. And depending on the relationship regarding the research and the mass market, sometimes we're more towards the research side or more towards the mass market. But we're always connected to those two spaces. So in some ways, we're kind of like the pre-applied technology group. The good thing about our position is that it enables us to have real-time information with the market, because regarding time, the scale in research and the scale in mass market is completely different. Where research, a lot of technologies and very exciting research that was discussed today, implementation can be 5, 10, 15, 20, 30 years. Whereas in big companies, you're looking at quarterly results, or what can we get in 18 months into market? And so this is kind of an interesting thing that helps us to work towards making some very small and palatable implementations of technology that makes commercial sense to mass market companies, so that they become more inclined to adopt this new technology and even and hopefully fund fundamental research. So I'll start to go through just a few of the technologies. Some of them are kind of basic diagrams, then some videos of some of the applications. So as I mentioned, we develop matrix materials and different processing techniques that enable us to tune a wide array of different attributes. And that's anything from tensile, modulus, and other mechanical properties, as well as haptic characteristics and durability, so UV resistance, abrasion resistance, scratch and mar resistance, just depending on what that commercial application is. And then we partner with companies and work to identify their specific needs so that we can deliver a custom version of our material to their application. So really, what's the difference between a traditional carbon composite and a flexible one? Essentially, flexible carbon fiber technology is unlike traditional carbon fiber composites that are limited in the bending radii for very thin laminate layers, where exceeding that bend radius results in resin and fiber breakage. So the key to our material and our technology is the very low shear modulus that allows compliance at the interface between the fiber and the resin. And this low shear modulus with a high elongation relieves the cracking and bending failures in traditional carbon fiber composites. Yet the carbon fiber tensile properties remain similar to traditional composites, since less than 10% of the resin strength contributes to the overall tensile strength of the composite. So as I mentioned, we utilize a variety of techniques to customize and tune flexible composites to harness carbon fiber's tensile strength in a flexible form. And you'll see it makes it to be really conducive for material transformation. So just to touch quickly upon the work that was a phase 1 in collaboration with a self-assembly lab, where we tuned carbon fiber in terms of just the stiffness and flexibility. And Skylar and Athena at the self-assembly lab were able to print a heat-activated polymer system onto our carbon in various patterns and orientations in order to induce a very predictable and controllable change in the material. I have the luxury of having Christoph Cross be the next presenter, and he'll actually talk about an application that was born from that collaboration. So what is tunable carbon fiber, and specifically relating to material transformation? And it's a carbon fiber composite that is designed to provide specific mechanical advantage in a given system in order to assist the desired material transformation. And we'll talk about now just a few different ways that we're able to do this. Once again, not just in a lab setting, but we're looking to scale into a production setting for some applications. Matrix placement, the ability to create zonal composites, shape memory, and to control the elasticity. So similar to Ying's, some of her slides, and here we're able to control not just across the width or across the top plane, but also the penetration of the matrix material into the carbon fiber. So if at the top you have one type of matrix material all the way impregnated, similar to a traditional carbon fiber composite, a second one down would be two different matrix materials impregnated equally in terms of depth. The third, two different matrix materials impregnated at different proportions, and the fourth, three different matrix materials impregnated in different ways. And with this, we can really control the symmetry of the material, making it more or less susceptible to transformation in different areas. We're also scaling up to be able to produce these in mass scale. So, zonally impregnating or coating carbon fiber, so we can have live hinges and do it in an abrupt change or in a gradual change to invoke more of a curling effect. This one's a little bit more exciting. We're now able to go from a sheet form into a preformed piece of carbon fiber that we're then able to flatten out, and then once the tension is relieved, it can pop back into a certain shape. And once again, this is work that we're looking to continue with Skylar and Athena in the self-assembly lab, where they can use different active systems in order to evoke a change given a stimulus versus what this example will be. And so just to show the example, we formed a cone with a flat nose out of carbon fiber and a cured epoxy system, a resin system. And then we flattened it out on a vacuum table and put just a thin sheet of polymer on top. And then this video will just show the vacuum being relieved and the carbon fiber composite turning back into its preformed shape. Or not. If my mouse will appear. Yeah. Okay. So we relieve the vacuum fairly slowly just to show the transformation, but if it was completely removed, it would have happened quicker. So once again, potential uses, flat packing goods, and just different, more exciting applications in terms of the performance side of things. The next is preferential fiber orientation, similar to what Ying was talking about as well, in terms of using different orientations and maybe cutting materials in different shifted degrees in order to have different properties. So this strain and load graph is all the same material, just in different fiber loading and different orientations. And we can really control the elasticity in the off-axis direction, providing points of locking the material out and the rebound as well. This next is just an example of that. As you'll see, we just have a material cycling back and forth. And once again, the idea is to be able to then incorporate an active material in the system so that we can so that it can happen, in situ in whatever application we're talking about. So once again, carbon fiber doesn't have any real elongation to speak of, and so of course this is just the matrix-dominated elongation. So kind of back to just this first slide, and I'll wrap up here. Is that my hope is for us to continue to kind of parse unique technologies that are coupled with our carbon fiber, our flexible carbon fiber technology, to enable that conduit to mass market as soon as possible. There's always that question of, well, how is this technology applicable? And we hope, or our hope is to get companies more, to make it more palatable and tangible for them. And with that, I'll end my presentation.
Thank you, Jonas, and let's invite Christoph Cross, Technology Program Leader at Airbus. And it wasn't by chance that we put you one after the other, of course.
Let's come back to the start. Okay, first I would like to introduce my function in Airbus. I'm working in a department called Emerging Technology and Concept, and our objective is to identify outside from classical aeronautical industry technologies or concepts that are not used on our aircraft, to imagine functions for these technologies and to prototype them, and then offer the possibility to the classical designers who are developing our aircraft to use them on our products. So it's a way of working that most of you seems to be classical, but it's true that in a huge company like Airbus, it's something more agile than we usually do. And what I will present you today, it's this kind of cooperation we had with the MIT, with Skylar, and with Junius on the use of programmable material on an aircraft application. So I will start with a bit of context. An aircraft is a very complex machine, very big and very complex machine. In particular, on an aircraft, you have many movable parts. First of all, you have the movables on the wing and the tails that are used to control the aircraft. You have an example here on A330 of an aileron, the aileron of a slat, which are used as the aileron is used to control the roll of the aircraft. You have also a lot of air inlets that are used to control flow inside the aircraft. It could be for cooling, it could be for air renewal, just for ventilation. The biggest one is what we call the rammer under the belly fairing of the aircraft, which is used for the renewal of the air in the cabin, so it's quite important. And most of the air inlets have a door which is actuated in order to control precisely the airflow which is going through the inlet. So it means it's additional complexity on the aircraft. Here, for instance, you have a close-up, very small close-up, half a meter. We are in the trailing edge of a wing on a A320, and you see you have actuators, which are hydraulic actuators with the feedings, with control cables. You have a shaft to control here it's to control the flaps of the aircraft. You have a lot of hinge with big bearings. So this is just a close-up. Just imagine that you have hundreds of systems like that on an aircraft. So in terms of system, it's very complex. It means that it's heavy. It means that it is expensive. It means that it needs a lot of care to ensure the reliability and the safety of the flight. So the question, why is this complexity? Could we imagine to have an aircraft simpler than that? An aircraft that could be as simple as a bird. A bird to fly needs to have bones for the structure, muscles and tendons for the actuation, and features for the aerodynamic. So apparently it's something which is quite simple, and we would like to imagine an aircraft having the same simplicity. So it's a classical biomimicry that most of you already mentioned during the previous presentations. Biomimicry applied to aircraft is not something new. First of all, the wings are mimetism from the wing of the birds, of course. But even when we come back to the early age of the aircraft, if we come back to the flyer, the Wright brothers use the wrapping of the wing to control the whole of the aircraft. So it's typically something that was a copy from what they observe from the birds. Today we don't use anymore this kind of system because our aircraft are heavier, are more and more heavy from a lot of time. So it means that the materials are stiff and it's not possible to modify the twist as they did themselves. But biomimicry on aircraft is just not copying the nature. If I take another example, so it's not a picture from the last Batman. It's a very old aircraft from the 19th century from Clément Ader called Avion. And this aircraft looks like really a bat, but it was not a good aircraft. It did not really fly. Why? Because it suffered from large drawbacks in terms of flight dynamics. So even if it looks like something which is similar to nature, it does not mean that it is work. Why? Because biomimicry means first observe a phenomenon in the nature. The second, which is important, is to understand what is the physics behind that. And the last one is to identify the process and the materials that will allow you to reproduce this phenomenon at the scale of an aircraft. It's something that was not done here. I can show you an example of what we are doing currently in Airbus or in other aircraft manufacturers also, which could be a good application of biomimicry, what we call the riblets. It comes from the observation from the sharks. Sharks are swimming very fast in the water. And they consume less power than it could be expected by the application of the simple hydrodynamics equations for their movement. And the reason is coming from these microstructures I have on the skin here, which is interacting with the vortices which are created as the contact between their skin and the water. So we observed that. It was explained by aerodynamicists, and we reproduced it on an aircraft by a similar structure, which was installed on the wing, on the tails, on the fuselage, on several parts of the aircraft. And it works. You have a huge benefit on drag and on fuel consumption, consequently, if you use such a system. Now we are on the step, which is the last one, how to install that on aircraft, is ensure its maintenance, ensure it will resist to water, ice, sand, and so on. But it's really an application for biomimicry. Much more interesting for us is biomimicry applied to the control of the flow of the aircraft, for the control of the aircraft. And it's what we used to call in our industry the morphing. So it's here that we see the programmable materials as really something which is very powerful. It can change the way we can do this kind of application. Airbus is engaged from decades now in morphing technologies in collaboration with a lot of laboratories. As an example, there is a project called SARIS2. So I'm sorry, the movie is not working on a Mac. I don't know why. So you have here the example on this project. So it's a big project. We are cooperating with 64 laboratories all over Europe. And here you have an example of a leading edge of a wing, which is actuated in order to change its shape, in order to adapt the shape of the leading edge to the speed and the angle of attack of the aircraft. So it's the first step to morphing, but the first step only because the actuation remains quite conventional and we want to work on that. Another example here. So here we try to mimic the movement of the feature of a bird. So it's a collaboration we have with two laboratories in Toulouse, one dedicated to aerodynamic and the second one to electroactuation. So you have an example here of the system which is installed in a wind tunnel. And you see, or you not see, but I tell you, that when you activate it, you have less mixing of the flow coming from the upper and the lower surface, and consequently, you have lower drag, so less fuel consumption. I don't explain you the equations. Pedro already did it, so it's OK. Voilà. So now, how to apply that really to an aircraft? So we met with Skylar several months ago, and we really think in Airbus that programmable material can have an interesting application. We started with a small application case, which is small means simple to take into consideration and to implement in an aircraft for a test. So I will, without going too much into detail, I will explain what we did. So this is an engine of an F330. An engine is packaged within something that we call a nacelle. The nacelle is for the aerodynamic shape, and it's also to protect what is all the system that you have around an engine. An engine is as complex as an aircraft, as you can imagine. And the inside of the nacelle needs to be ventilated for various reasons. So it means that on the nacelle itself, you have an air inlet, which is above or on the side. And you can see it here, for instance. So you have a close-up, a view, which is approximately this kind of thing. So it's a small system compared to the size of the aircraft. So you have a penalty in terms of drag, you can imagine, but it is very small. So there is no reason to install an actuator to modify the door position, to modify the size of the inlet, and thus to modify the air going through the nacelle. In fact, the benefit you will have in terms of drag will be counterbalanced by the additional weight and penalty we have to the aircraft. Nevertheless, there is a potential for drag reduction. We are speaking about 0.1% fuel consumption. It might not appear to be a lot, but on a current aircraft, which is quite very optimized, 0.1% fuel reduction is a lot. It is the margin of the airlines. So, we thought about a simple application using the usual way we work. In fact, instead of having something completely fixed, we created a prototype here with a scoop, which is a stiff carbon plate. And we use the Bernoulli principle. The Bernoulli tells us that when you have a variation of speed, you have a variation of pressure. So if you don't have the same pressure between the two faces of the scoop, you create a suction force that modifies the position of the scoop. So it's what we did. We did wonderful simulation. In simulation, it works perfectly. And we put the system on the aircraft. And on the aircraft, it does not work. It does not work because the condition that's always perfect when you are in simulation, when you are in the real life, the air around the aircraft is not perfectly stable. You always have some leaks on the lateral side of the plate because you can't have perfect control of the distance between the case and the plate, and so on and so on. So it does not work. And the consequence is that the plate is going into vibration. So it definitely does not work. So the question, the idea behind that was to say, OK, why not asking the plate to go either in closed, either in open position, and that's all. We do not want to authorize them to go into an intermediate position. It's typically what we could do with programmable material. I asked the question to Skylar, and he came back to me with this sample. So you have it bigger here. So it's typically a carbon plate which was provided by Carbitex, where some additional device printing parts here that it is on the wrong side. It's funny. And the consequence is that you can have only two positions, equilibrium position on this plate, thanks to the system. So intermediate position can be balanced. So we install that on the prototype. You recognize, so it's at a scale of 2/3 the system. On a wind tunnel, so it's a low-speed wind tunnel, of course. For the first test, we don't do it at a transonic speed. And we tried it. So we accelerated, suspense. And at a certain speed, you will see the transition between one and the other position. So we repeated it, and each time, precisely at 15 meters per second, you have this transition that operated perfectly. So it shows that the principle works. So we're very happy with that. And now the next step, we are working with the guys in charge of nacelle in Airbus in order to specify what could be this plate, this scoop, for a transonic application. And we'll go to another test later on, always in collaboration with Skylar. Voilà. But for us, it is the beginning, really. We think that this application could also be used, this kind of application could be used for other movables. We think in particular to all the control surfaces you have on an aircraft. And we will discuss the possibility to apply them now on other systems such as the rudder, which has the very vertical part here, or the aileron. If we success, for sure, it will drastically change the way we will design our future aircraft. Thank you.
Thank you, Christophe. And our last speaker is also Christophe. Christophe Gouberin is a product designer practicing in Switzerland, and he was recently a visiting researcher at MIT.
Oh, what? Okay, there is trouble now. First, thanks, Christophe, for getting the audience using to the French accent. And by the way, I'm also Christophe Gouberin. I'm a product designer, but I come from Switzerland, the French part. No, do you think? Okay. Because yeah. Yeah. Well. Okay. I'm Christophe Gouberin. I'm a product designer, and today I'm be glad to present you my work involve product and experiment. I work on my one design studio office with my colleague Carlo in the Swiss mountain. Our Aerospace reflects the way we work. On the right side, on focus on product design, we work for some different company like Alessi. This is an Italian company. I work for Swiss Airline to rethink the first class service. I'm a Swiss, and as a good Swiss, I work for a chocolate company. We work also for chef and to make some kitchen tools. That's why I learned during my study in design product. And most of the time when we work for a company, the company give you the condition, such as material, the process, and the customer experience. But for me, as a designer, I think it's really important to question this condition. Why? That's why we have the left side, where we focus on research and experiment. In this side, we try to rethink the way how we use the material, rethink the production of process, rethink the way how the people interact with the product, rethink the way how we use a material. Let's say with the paper, for example. Intuitively, we will avoid water on paper because paper in contact with the water starts to deform. But I was so fascinated about this kind of effect and the way to exploit it. First, I tried to work with sample tools, and I buy a ton of paper, different paper, and I try to understand this kind of effect. I discovered that the tracing paper works pretty well with the water. So I decided to take my desktop printer and put some water inside. And this idea, it's I want to control this effect and make a process, but maybe will be more clear with the video. I don't know if you need the song, maybe not. Yeah. There is no sound. And first, I take my computer and I just design some line on the InDesign, the really basic software. You can see the cartridges where I just put some tape water inside. And after that, when you print on the paper, the fiber of the paper will start to dry after 3 minutes, and the paper starts to bond by itself. Of course, we can print on both sides. And yeah, after that, you just have to wait, and the paper moves by itself. An interesting thing for me was also to work on the curve. That's something, and maybe Eric can say that, it's quite hard to make a curve by hand. I also work on the large scale. It's approximately 80 centimeters high. I don't know how many inch, but something like that. And because I'm a product designer and the product designer make a chair, I tried to make a chair too. And yeah, the failure was the chair, it's only like that, but I continue to work on. An interesting aspect for me, it's the production process of making an object. By vacuum sealing printer, we can imagine shipping flat an object, and the last step of the creating of an object will be done at home. When the user opens the packaging, the object can fold by itself. Another thing also, that's how the people can interact with the product, how the user could be part of the production process, be influencing the final shape. If you open the object on the corner, for example, the object will fold on the corner. It means you can play with this object, and the object can interact with you or with your environment. So Hydrofold was the project brought me to MIT, to Boston. Thanks again, Eric Demain, and give me the possibility to discover other projects, other people with similar passion. For example, Skylar Tibis. And we start to work on the active material. For me, after my experiment with the paper and as a designer, I really want to work with another material. I mean, paper, it's interesting, but the wood could be really become more stronger, and you can really imagine do a product with. That's what we try to do with Skylar, and to rethink how you can organize the fiber of the wood. And that's the same one of the paper. When the wood can start to dry, if you put on the water, you can imagine if you reorganize the fiber, the wood can fall in the way you want. You can imagine to rethink about the imp chair, maybe. Another project, it's also, I love the idea, you can just bring and process it to try to do another thing with. I mean, we try on the 3D printer to print on the textile. We just stretch the textile and we print on. And when you retract the textile, the shape starts to become and to fall. That's also a really interesting thing in terms of product. You can imagine to shipping flat and the object emerge. Now, what we try to do in this office is to play between the left side and the right side. means between the product and the research. Actually, many companies are asking for if we can design an object and shipping by internet. That seems it's quite the trend in Europe actually. And actually, I think it's a good opportunity to work with this kind of technology. We currently work on the chair that we can imagine to stretch the textile, to print on, and when you get at home, you can imagine to retract the textile and the shape of the chair emerge. As a designer, I think it's also important when you use this kind of technique, for example, the textile, that you can use the textile also for this other property, let's say for comfort and for the flexibility of the chair too. We work for a light company, and the idea of this project, it's really new. You can play with the intensity of the light, depending how much the textile are stretched. We work for a shoe company and try to mix some different material with the 3D printer and print on the textile. There is a lot of different textile, and when you 3D print on the flat, after that, the shoes can fold by itself. Another thing could be, and we try to work on that with Skylar, an active textile, and that we can imagine the shoes can retract around your feet and just become the perfect ergonomy. That's everything become to change my vision of making a product and can just change the way how we can have a size like, let's say, the commercial size M, S, XL, and some other size. Merci. And
so we invite all the speakers up to the table for a discussion. So I guess I'm a bit biased in this session, given that we're collaborating with many people here. So I'll try to be a bit agnostic. But what I found quite interesting in the session is the transition from the beginning to the end, hence the research to the application. And often talking with lots of my colleagues, both in academia and outside, there seems to be this constant tension where the academics think we shouldn't work with industry too much because we're going to be way too applied. We're going to be pushed to this spectrum where we lose our freedom. We're going to be really focused on solving incremental problems. And the other side, industry looks at researchers and said, you guys take way too long. How long is it going to be to implement? You guys are crazy and irrelevant. What are you talking about? And both directions are totally wrong or can be wrong. And so what I'm really interested in is how we can find useful intersections. And I guess I would pose it to you guys to think about what can we dream of as the ideal intersection of those? How do those two collaborate so that it doesn't take forever and that we aren't producing just totally irrelevant things, but industry isn't also pigeonholing us? And I hope what was shown was kind of an opportunity to see where it's been super useful from our end and seemingly useful from the other end. But maybe we can talk about that. Do you guys see any ideal opportunities there to collaborate on industry and academia?
Yeah, so maybe I can take that. So, I mean, we here at MIT that has such a strong tradition of interacting closely with industry. And so my personal experience in our lab has been that often industry has come to us with very interesting and challenging problems. That can be turned into academic problems on themselves, and then once you understand what you need to understand, they can be taken back, and that has been extremely valuable for us. I mean, the time scale is certainly an issue, but this is where it comes on trying to join different cultures and making sure that everyone understands the other. But I think there's enormous opportunities.
Yeah, I think it's getting buy-in from industry where sometimes this groundbreaking technology, whatever it may be, is so invasive to big industry's current manufacturing processes. And so just, taking just small components, even though it, in ways that it doesn't detract or focus the research or pigeonhole the research where, so I guess from our perspective, we're not trying to say, okay, we only need research in active materials in this one space. It's, what can be done, and then for us just to be very perceptive and work with companies to try to understand their process and see what we can do to incorporate something that's minimally invasive into their manufacturing process. And over time, I think that buy-in just kind of grows, where they'll start to really see the big picture. Because that timeline really is a big problem when, once again, big companies are looking at quarterly and yearly, progress.
The difficulty is that in industry, when we arrive with a problem, we want a solution. So it means that collaborating with a center of research, whatever it is, it's really interesting. Sometimes it opens doors that we would not have imagined before. But as you say, this door maybe are going nowhere. So we have to accept that. So it means that we have to maybe to launch in parallel several studies in order to find the right one. But giving the liberty, the freedom, to the researcher, also to continue to search on the way you want to search.
Maybe one additional question to bring it back to the theme of this session in terms of material transformations. If you look at graphene folding and kirigami to dimpling on golf balls up to like big components on planes, this is like a huge range of potentially similar transformations, geometrically at least. How can we share tools, capabilities, knowledge, given that, Paul, you were talking about how transformations can scale, at least in paper. How can we share that, software tools, knowledge tools? Are there opportunities for convergence there?
Well, speaking for me, I think as we learn to do a few things, we get to the point where suddenly you want to start designing stuff, and you start to need these kinds of tools, and we don't have them, nor do we really want to build them. We would rather work with designers. And I should say, this idea of a suite of tools that are, sort of modules of programmable matter to do something. You could do a certain signal and cause something to bend, and then use that to design a whole structure. A lot of that is very generic, and so we want you to hurry up and get these tools together so that we can use them.
Good thing we have Autodesk in the audience, probably. But we've been thinking about that a lot. How do you create a language or different functional modules of folding, curling, twisting, bending, cuts, and therefore can propagate them? These are like abstracted principles that we could look at with different materials and different scales. Yeah. Pedro, did you?
Yeah, I was going to say, one difference I see between a number of the talks in this session compared to the more design creative-oriented talks, well, Christophe was very creative, but some of the other creative-oriented talks that we saw earlier today is that I guess to make all the leap to industry, you really have to understand what's happening from a predictive perspective. So you need to have solid models that can then be implemented with software. Software won't run out of thin air, so it needs mechanistic principles, it needs theories, and that's really the challenge. How do you go from highly geometrically complicated problems like what Paul was showing into a way that then how to scale it up to the scale of an airplane? And I think that's a challenge that is necessary to port this boundary. And of course, the process of discovery, even before you have that understanding, is extremely important. This communication with designers can really take us there, right? So there's a whole spectrum across, but theory and mechanics is crucial if you are to then develop predictive design guiding principles.
Yeah, just to amplify on that, the kinds of problems that we're talking about are the ones that will cause your standard simulation packages to choke and fall apart and die, right? These are very hard problems.
Yeah, often one of the first questions we get is like, how do you simulate this stuff? And then we often collaborate with people, both researchers and industry, and right away you're like, oh crap, we're out of the range of many, many, many things. So you have to invent the tool to simulate while you're inventing the other thing, and you're then trying to invent the machine to make the thing that simulate. You're like trying to balance all of these domains, but maybe at another scale it has worked and there is a tool to do it, and we just don't know it at our scale with our material, but we could translate some of the principles. I'm definitely interested in that. maybe we turn it over. Does anyone have questions from the audience? Heinrich, in the back, Mike.
Maybe just more an observation rather than a question. Particularly in contrast with the last session, it's really clear that in this session, you focused on, not so much on the material itself, but really on geometry, right? And so when Skylar, when you said, so what is the underlying or the overarching principle? It seems to be geometry. And how, what kind of geometrical changes can I put in the material? And so actually that relates to math. And then the question is, are you talking about geometry or topology at some level?
Maybe just a comment to your comment. It's true that if I speak about application to an aircraft of active matter, so what's important for us is not the material itself, it is the effect he has on the flow. So as you say, clearly it's the geometry which is important. It's true, yes.
I guess another comment as well, because we're more tied to the industry part as well, it's not just, I mean, of course, you need to have the geometries because that's the material transformation. But then on top of that, what are the application-specific, mechanical properties that are needed? So the stiffness, the time to transform, what environment is it going to be in? And so that's a whole other subset of criteria apart from the geometries that's also important in making these a viable, making material transformation a viable, technology.
I'm wondering if you could talk about your mental model of what tools of the future would look like. And as I compare and contrast the various techniques and approaches and material, I just, we have a bewildering array of scales and types of activities, and processes. And so, are the kinds of tools that would be useful to you and other people here, would they be sort of point solution tools, little apps? Would there be kind of a deep infrastructure, a systems-based model? And I think just so love for you to kind of speculate on what this would look like. And finally, knowing, of course, that with every generation, every couple of years, you'll be reinventing new types of methodologies. How would one incorporate that? So riff on tools.
So maybe I can comment. So Subra Suresh, who was the former Dean of Engineering here at MIT, kept saying that engineering is about invention and reinvention. So sometimes going back and revisiting old tools can be very valuable when you put them into a new context. And so, for example, in terms of tools in our lab, we've had a huge amount of success interacting with computer graphics. And so some colleagues from Columbia University, from the group of Ethan Greenspan, who are leading experts on developing software for animation movies for Pixar, Disney, and all those studios, where, according to him, the most challenging aspect in those simulations are animations are typically reproducing realistic visualizations of hair and cloth. Which are slender, they can undergo complex geometries, coming back to something that Hiring mentioned. And the eye is a very good filter of picking what's realistic and not. And when you're thinking about geometry, you really have to capture the mechanics very accurately. And so we've actually went to them and ported tools from animation, turned them into engineering, and we found, and no one knew, including the people who had created them, that they had incredible predictive power. And that was certainly not expected. And we now, that we have the tools in-house, we're using them to study many other problems. And so sometimes the solution might not just lie down the corridor from your expert colleagues. They could come from a different field. And that's why I think such a workshop is so exciting, because perhaps some of these connections might be established.
What kind of tools are you referring to specifically? Software and physical, hard tools in manufacturing, or?
Yeah, both. So how do you tools for the purpose of democratizing these practices? Because many of you are researchers, or you're working in really refined areas. But to make this more accessible, should we want to do this, we would need tools that would be more accessible. So what would those tools look like? Digital, physical, even conceptual tools?
I guess, yeah. I can speak on the manufacturing side a little bit if that helps. So I think simplifying the end manufacturing and putting more of the onus on the material manufacturer. So right now, I think since 2001, like 42,000 manufacturing businesses left the U.S. And this is my economist kind of coming out of me, I guess. But and it's because a lot of those companies were transactional manufacturers where a company designs a part out of a polymer or metal, whatever it may be, send it out to a bid, and then they just choose the lowest price, all things equal. And so, of course, labor rate's a big factor there. But if we can start really designing these materials, then potentially the manufacturability is more, passive heat to transform, reducing a product that's 40 or 50 components down to 12, and instead of 15 different processes to incorporate them, it's 3. And then I think the labor rate becomes more of a moot point, and potentially manufacturing can happen differently in the sense of at what stage the product's manufactured in, less of a final assembly, more of on the material side. And then you can place a factory theoretically maybe anywhere in the world for logistic reasons versus like a labor rate.
Okay, so we are going to wrap up the panel. We're going to transition into a discussion with Mert Flemings and Philip and Leela, but we need to switch mics. So hold on for a few minutes. You can talk between yourselves. We'll switch mics and then continue the discussion.
In a minute. Yeah. Yeah. Do you wanna?
Can we get it to the table?
What that, you could do?
It's all right, I have my own notes, I'll figure it out. Yeah, don't worry.
Okay. So please welcome Mert Flemings, Toyota Professor Emeritus at MIT, in a discussion with Philip Curry, Associate Provost at MIT.
Good. Oh, thank you. Thank you. Yeah.
Shake your hand.
Nice to see you. Yes. So it's a privilege to introduce my colleague and friend, Mert Flemings. Mert has been here, I don't know if it comes out, but he's been at MIT over 60 years. He came here as a teenager to study. In 1947, I believe, he entered as a freshman, got his first degree in 51, and a few years later, very few years later, he got his doctorate. And he's been here really almost ever since.
Except for 2 years in a real foundry.
In a real foundry. He actually knows what a foundry is. And well, here are his degrees right here. Here he is at a certain moment in time. Sorry, I don't want to embarrass him. This is all unrehearsed. You have to understand this. So, but those are his degrees. And, you know, he had an enormous impact on the areas of applied properties of solidification, modern industrial foundry practices. In fact, my one road trip with Mert to do some development work for the humanities, arts, and social sciences was to a foundry up in Peterborough in the New Hampshire area. And Mert led me and a few of my colleagues, we knew nothing, by the hand. He came here when there was a department of metallurgy, and he, as much as anyone I know, was involved in the transformation and expansion of that great department into our material sciences and engineering department. And, you know, I don't want to boast, it's not my department, but it's been ranked forever as the leading department in this country, and I would bet among the leading, if not the leading, in the world today. And it's been there a long time, and this gentleman has had a lot to do with that in the recruitment of faculty, in the development of our graduate programs, and it's just been so vital to this institution. And I heard the name of Subra Suresh mentioned in the last session, and of course, another fabulous material scientist in that department, that Mert, who was chair of the department before he became Dean of Engineering, and Mert was for many years chair. He also had a great deal to do with the creation of the Material Processing Center at MIT. Simply put, this center has been a dynamic division, research, interdisciplinary center at the Institute. And just, I believe on April 13th, we had a little dedication, and it was named after Mert Flemings, which is just a wonderful honor. Let me say something. It's very rare, but his students, the products of his work, have come back to this institution time and again, and there are 2 endowed professorships named for Mert Flemings in his department. They're graduate fellowships. There's this remarkable center, and this summit is dedicated to him. So we love honoring you, Mert, and for good reason. I mentioned the department. This is his bride, Elizabeth, who is with us today, and we'll be seeing more of her later. I don't know who that is. He looks like a politician, though, Mert. Can you, the man on your left, on my left, and Lemelson. So the Lemelson program here, Mert had a great deal to do with launching. It's all about getting young people, students, engaged in the world of invention and innovation. Numerous things have sprung from this, and even our president has been involved, it turns out. It looks like President Obama bicycling through Lemelson. I mentioned the Material Processing Center, and this is Mert. And what I want to do, and I have no expertise in this area, is ask Mert a few questions. I sent these questions to him very late at night, last night, and he responded with a few edits this morning, which, you know, you wake up to Mert. So let me start by asking, so this department, the world of materials has changed, and you've seen it over the 60 years develop in the way it has. And the talks today, of course, amply demonstrate where we are, state of the art, how we look to the future. Tell us a little about what metallurgy and the world of materials was back in '06, back in the late 40s when you arrived here as a freshman.
Okay, but Phil, before I get into that, let me make a few comments about where I hope to end up at the end of this comments, and that is to say what a wonderful meeting this is. Yeah. I've had a whole new look after 60 years. I didn't think I was ready for. I didn't expect to have some new kind of look at the field. But this is a different way of looking at it, an important way of looking at it. And it's really quite exciting for me, and I thank all of you who are here and the people who've arranged it and cast, and I may have something to say at the end. But to come to your question, right, I came here, as you point out, in 1947, and in those years of my undergraduate and graduate education, and even the beginning of my faculty years. As you say, we were a metallurgy department, and the best I could describe the way we looked at our field when we thought about what the department was and what we were supposed to do. We thought in terms of what today we'd call a materials circle. The material, in our case, a metal, begins with an ore in the earth, and so you start with mining, and then you've got preliminary purification, we call beneficiation. Then it goes to a smelting operation with the chemical refining and the melting, and then on to making parts and then to using the parts, and finally to recycling or in the ground back to where it came from. And our department was kind of organized that way. We didn't have mining anymore when I got here, but we had not much before that. But the next step we had a leading laboratory in mineral beneficiation. And in case you're not up on mineral beneficiation or ore beneficiation, that's when you dig a lot of stuff out of the ground like iron ore. The first step, you don't just get pure iron ore, you don't just get pure iron oxide. You get a lot of sand and cement and, clay and everything else. And to the extent you can separate the two, you want to do that, and you do that by big jaw crushers or rolls, and then hoping to get it down at a granular size, and then you use flotation process or other processes to separate the light from the heavy. And we had, as I say, a leading laboratory, probably the leading laboratory in the country doing that. And we had the big machines to do all those things. Next step is smelting, and we had that. We had large furnaces for refining copper down in the basement of Building 8. Somewhat smaller apparatus for doing iron. We had a chemist who came in, John Chipman, who came in and brought chemistry, and he kind of led the way to studying some of these big processes on a smaller scale. But we had that. Then we had a forging operation and a welding operation, and we had my big foundry that I came to. It was going when I got back to MIT. It was going when I was a student. And we had 300-pound induction furnace and a 500-pound arc furnace and large melting and molding equipment. So that was that. And then we got into the 60s, and all of us, I think even those of us who had big equipment, realized that this is not where engineering was going, that we could use the facilities, we could teach our students better by moving more to engineering science. And that was the beginning of of a pendulum that swung toward engineering science for many, many years, and properly so. We stopped working on problems narrowly focused to immediate needs of specific industries, like the foundry industry. And we moved to broader problems, problems with an engineering science base, but hopefully with one foot on really practical things too, because after all, we're an engineering school, to use that science to develop stronger underpinnings, not just narrowly for a single industry, but that would be applicable broadly to many industries, and hence my own move gradually from direct foundry practice on into the solidification area, which would have more general applicability. And then we began to view our department with a different kind of model, not this materials circle. But the new model we kind of began to get in our mind was we used a tetrahedron. And we divided the field in our minds into 4 discrete parts, representing each corner of the tetrahedron. And we used the tetrahedron in our schematic model because, as you well know, every point on a tetrahedron is connected with all of the other 3 points. And we wanted to make the point that these 3 areas of our field were intimately interconnected. So what were they? Structure, which you've talked about very much today, structure from the atomic, even sometimes subatomic today, but certainly atomic, molecular, crystalline, nanocrystalline today, on up to the microscopic and the macroscopic, and I guess the civil engineers, I think I heard this morning talking about mesoscopic, but structure was important, and we worked on what that structure was. We worked on instrumentation to learn more about structure. We worked especially on structure-property relations, and that was the next point of the triangle. To achieve properties, the different properties we want in materials, what you're talking about here today, and we talk about so much in our field. If you want to get a set of properties, you need a structure to achieve those properties. Then the next point on our tetrahedron is performance, and I won't go into that too much, except just to say that it isn't enough to make a strong piece of metal or ceramic or polymer, but it has to perform in the right way in an electronic device or in an airplane or an automobile. And the final one, back to my home, is processing. In order to end up with a part that performs properly, you have to manipulate the structure to achieve those properties, and that is one way to look at processing. And with this kind of model, we could then incorporate other materials. We were no longer a metallurgy department. As Phil says, it isn't easy to move a department, not even to move your own field from a narrow field to a broader field, or to move the structure of a department from one staffed only with people with a metallurgy background, but broadly in all materials. And that has gone on consistently ever since those days in the late 1960s, and continues today as the department evolves with greater strength and greater interactions, of course, in the biomaterials field. So I think that's my simple summary. If I just conclude by saying, if I were to look at threads that go through those years, one of them is certainly the basic science and basic engineering science, but the other, as I guess I've mentioned already, is one foot on practice, on useful engineering. In the early days, that meant interacting with existing large industries. Today, it means more and more invention and innovation and entrepreneurship, starting with and working with smaller companies.
Good, great. So you made your name in solidification, in casting, elected into the American Academy, the National Academy. You've written 300 or more articles, seminal textbooks in the field. When you look at those fields, where's the action today? Is there action? And how have you seen those two areas that you yourself have put quite a stamp on? How have they evolved?
Well, those, you know, you're right. I began at least the first 3 or 4 or 5 years in my undergraduate, or 3 or 4 years plus my undergraduate, were in the direct foundry, practical foundry area. And later and those fields have continued. I want to come back to that in a minute. We then moved on to the solidification and took our ideas about solidification from the foundry practice and applied them, combined with them with ideas that the crystal growers were developing about crystal growing, and worked for growing, for example, the kinds of semiconductor single crystals that became so important beginning in the late 1950s. We worked on our ideas of structure of controlling structure of solidified materials, and today one of the most important applications of let's say very advanced control of how the crystals grow inside an engineering component, a structural engineering component, is the manufacture of turbine blades for aircraft and now for power generation as well, where the foundry through very sophisticated equipment produced castings blades this long, with beautiful single crystals growing up all the way, or for the best of them, with just one single crystal growing all the way up. Now it's not a homogeneous single crystal like a diamond, but it's one single big dendrite. You'd love it if you haven't ever seen it. They're beautiful, some of the structures that you have here. And those and of course, solidification now is a vital concern in many areas of electronic manufacture, where you're involving liquids in one and liquid solid transformations in one or another of the processes that you have. And of course, batteries, so important today, are a solidification and melting problem, if you want to look at it that way, for many of them. I had wanted, I won't go too much, I think I take too long time answering your questions, but especially if Ron Kurtz had been here.
He just walked in.
I was going to, so as long as
Carol with him.
As long as Ron and Carol are here,
come on down.
I'm going to take your time to go back from the modern solidification and its application in turbine blades and goodness knows what, and talk about one of my favorite research activities that we did, and I think probably one of Ron's favorite ones too, if I remember rightly. And one I think will interest some of you if you don't know about it. At that time, and that would be a long time ago, an artist connected with us, a sculptor connected with us, and to make a long story short, he said that he had an invention that he thought had some practical engineering usefulness, and what did we think of it? And we looked at it and said, well, I don't know whether that has any engineering applications, but it certainly is a wonderful way to make sculpture. We thought, not being sculpture people, but we got then a grant from the Rockefeller Foundation and later for the Ford Foundation. And this artist, Al Duca, then worked with us for the next 2 or 3 years, developing the process to the point where it became feasible in practice, and producing sculpture. And we had a series of conferences where artists came and worked with us, came and worked with Al and learned what we were doing. So I'll tell you what this was all about, and I'll just back up only this much to say that I'm sure almost everybody will understand the lost wax process that for making sculpture, or today for making important aircraft parts and automobile parts in high production. But in the case of art, the artist will begin one way or another with a wax form. He may start with something else, but he'll ultimately end up with a wax form, he or she, with a wax form that'll be a precise replica of what he or she wants in bronze or stainless steel. And then the next job is to encase that in ceramic. Today we mostly use shell ceramic, so we'll take that wax and we'll dip it in a ceramic slurry, and then we'll dip it in a fluidized bed of ceramic, and we'll build up a ceramic shell. Then we put it in an oven and heat it up, melt out, and then burn out the wax. And then we have a mold, and we pour the metal in. Very simple. But it is expensive, and it does take time. And Duca's idea was that, look, for some kinds of sculpture, we can skip all that. And here's what he did. He take a big block of styrofoam and carve his sculpture in it, and polish the edges and smooth it all with sandpaper or a file, and then put that in a box and pour dry sand all around it with a little bit of styrofoam poking up the top. So mind you, there's no big furnaces, there's no ceramic dipping, there's nothing but just cold sand around a styrofoam pattern. And then you pour the metal in, and as the metal goes in, the styrofoam burns out, and there you have your final casting. Well, it's not going to put lost wax out of business because it's got kind of a rough surface, and you can't make a gold ring for your sweetheart that way. But for outdoor rough sculpture, and by the way, the process has been developed, continues to be widely used today. Major application is for small engine components. General Motors has had an operation running for many years. I think it'll be superseded soon, but making engine blocks this way. So that was a long enough answer to your question. Too long.
Wonderful, but right on the mark. So I just want to introduce Ron and Carol Kurtz. They just walked in. So you know how universities work. The Center for Art, Science, and Technology is sponsoring this summit, but we wouldn't exist if it weren't for sponsors of our center, and the Kurtzes, Ron, an alumnus, a former student of Mert's, is funding this for us, and we're just really grateful. You will see more tomorrow, but it's just been a fabulous show so far, and you'll hear more about it this evening. But thank you for being with us, Ron, Carol. Thank you. Let me just shift a bit. I was going to ask you about Material Processing Center, but we can come back to that if time permits. But a little about the Lemelson MIT program that you've directed. So competitions today are legion at this institution, at all institutions. But there weren't a lot, and Lemelson was one of the first, the progenitor of these kinds of competitions, young people developing ideas that can, who knows, maybe get to market one day. And I just thought you might tell us a little about how that worked, how you see it evolving.
Well, Jerry Lemelson, some of you would know, was an extremely prolific inventor. And when in his very later years, he decided he wanted to begin giving it back, and he set up a foundation before he died, the Lemelson Foundation, to promote invention. And even while he was alive, he established a program here at MIT, based in the Sloan School, which stayed there for a few years, and then moved to the engineering school, and that's when I became the director of it. At that time, the prize, at that time, the Lemelson program, the sole activity of the program was to award a $500,000, $500,000 prize to the best inventor, the best invention, the best inventor of the year in the United States. And the whole aim was to, what Jerry often said, was to raise the status of the invention in the eyes of young people. And that prize continues, and it continues to be important. But we felt, and I felt when I took it over, that that there could be other things that the program could do. And the next year we instituted this contest for college students, which continues today, a little modified in character, but continues. And then soon after that, we instituted something that I think in retrospect is even more important, and certainly important. And that was a program in high schools, not a prize for invention that they'd done, but a stipend to permit them to form groups to invent things. And that continues today with some 15 schools now in the program at a $10,000 stipend each year, and their teams have formed on their own volition, working with a teacher or advisor, inventing something. And every year, by the way, you saw President Obama there. The reason for that is that every year since there's been a what do you call it, a president's science forum, that's not quite the right word. Every year since there's been that, there's been a Lemelson team represented among many other high schools in that particular operation.
Yeah, so that's been a real success. So you talked about sculpture, and you wear many hats and always have, and the arts are extremely important to you. You have been active in promoting the arts, I think principally of the Silk Road project, Yo-Yo Ma's remarkable orchestration of life. I mean, as only he can do, and you chaired that for a number of years. We almost got it to come to MIT. We failed, but we tried to have it housed here. It's now, after many years, permutations, it's housed across river at Harvard, right, near Soldier Field. But how did you come to the arts? I mean, was this always in the bloodstream? Did MIT help in any way through your education, shape you? Did it come independently? Maybe Elizabeth had something to do with it.
Well, you've hit it all.
She did, I know, but
you've hit it all.
Okay.
Certainly, MIT had something to do with it. I can say without shame that the best course I took at MIT was a literature course. I'm sorry to say the title was Books and Men, but it would be a similar course with a different name today. And it was
that was that era.
It was the era, and it was wonderful. I'm sure there were other kinds of instances, even though the education at MIT in those days was a good deal narrower than it is today. But there must have been other instances, like Al Duca showing up at a very good time. But I think beyond that, as you can well understand, is that my wife is an art historian with roots in Asia and Europe, and we have had a lot of connection with art over the years.
Wonderful, wonderful. So may I just quote, this is MIT, and CAST is the Center for Art, Science, and Technology. In my humble opinion, MIT's, I don't want to use this term, but I'm going to, comparative advantage in the arts is at the intersections of art, science, and technology. And we have been engaged in that world for a long time, and we're actually very well known for it, though our peers are getting more and more interested and are following us, and that's good. It's healthy for the arts. Yo-Yo, a Harvard man, said, and I quote, this is actually on the Silk Road website, "A new way of thinking is possible, a new consciousness, perhaps a new enlightenment. That brings the arts and science back together." What do you think of this convergence? You've been watching it, you've been on the margins of it, you've seen it, you know, as close as you can get with working with this sculptor. Are we heading down the right direction? Are we on the right path, or do we need to shift some? In what is required?
You know, when Yo-Yo said that, he was picturing, as I'm sure you understand, the era of the late 1500s, the early 1600s, when art and science seemed to be all together, in the times of Leonardo da Vinci and others. And I don't think, well, I know that he wasn't pretending there that we were all going to be Renaissance men in that sense. But I think he believes, as I believe, that what we may have lost by the enormous amount of information and knowledge and understanding and humanities that we have to encompass, what we may have lost by that growth in the scope of what our world is, we still have much to gain by bringing these disparate parts of our, well, they aren't disparate parts, by bringing these parts of our society more closely together. And I have, Phil, I have 3 of the most marvelous jobs that any retired person can have, and all of them unpaid. I sit, as you point out, on the board of the project and as treasurer of that project, and look at the excitement of what he describes, the excitement of the kids, and what he describes as the passive. What do I want to say? Not passive, but passion-driven education that they're getting by bringing the arts into the rest of the curriculum. I'm the treasurer of an elementary school that my wife and daughter have begun, also unpaid, and see what those kids are getting out of what I guess these days we refer to as STEAM education, STEM with an A, STEM with an art.
We like that very much, by the way, and we're promoting STEAM.
Yeah, good.
Yeah.
And finally, I still get to keep a desk at MIT and come in and keep watch over what goes on at times like this, and what CAST is doing. And you and Leela and everyone who supports you can understand that while they may not, while they don't even want to turn out Renaissance men or women, they're going to turn out students and people and researchers more qualified not only to do their own professional work, but to lead better lives.
We love hearing that. And you may not know it, but Leela Kinney keeps the data bank for us. For the last 5 years, undergraduate admissions, 80% of our entering class have had profound engagement in the arts before they got here. And that is, I don't want to say a sea change, but quite a dramatic change over the decades. So this place is attracting students for engineering and science, certainly for management, but for other things as well. And it's more than just rounding. And I just should say that the leadership of the arts, the faculty leadership, staff, senior staff, Creative Arts Council, I don't know how long you served representing the School of Engineering, but I personally was just grateful to have you at that table all those years.
I enjoyed every minute of it.
It was fun, but I mean, just having your wisdom there. So I don't know. Actually, I think we've run out of time. It's hard to see anything. Yes, we've run out of time, have we, Skylar? I was going to say if there was time for anyone in the audience to.
No, we have time.
We do?
We
have
can
a
open
minute
it
or
up
two?
if anyone has
Anyone
questions.
wish to pepper Professor Flemings with a question or comment? Don't be shy. Well, I think you've wowed them. Mert, thank you very much, really.
Thank you.
Thank you very much. Honor.
So thank you, Philip. Thank you, Mert. Thank you, Ron and Carol. It's been an amazing day. I think everyone, including myself, is probably just tired and overwhelmed and mind blown by all the stuff we've seen. So we'll end today. Tomorrow, we'll start the first session at the same time. So we hope you can join us tomorrow. It's also going to be webcast, so you can join online. One piece of housekeeping, anyone who has an electronic badge, please remember to return it. We need to keep those. Otherwise, we owe a lot of money, so that's not good. But yeah, we hope everyone enjoyed it today. Hopefully, we can continue the discussion tomorrow. Thank you again.